So to start with, I taught you a ton of things yesterday, and I'm going to catch you up on some of the many little things that you're supposed to know. So if I had a vector that was here, or it was here, and it's the exact same length, and it's going the exact same direction, aren't they the same exact thing? So if I was going to give a vector description for this, I would say that it's over 4 and up 2. And I'd like you to write this vector, we're going to call it vector V. I'd like you to give it 2 different names. You can't just say V. I mean like with numbers. There's a column way to do it, and there is a position vector way to do it. All right, Robbie, give me one of the 2 ways.
4, 2.
Like in a column.
Yeah.
Good. And what's the other way?
I 4i plus 2j.
Yep. And if this was in 3 dimensions, if it was like coming out towards you, just like an inch, 1, then we just add an extra 1 here, and then we'd add an extra plus 1k. I, j, and k are the 3 letters that we use for these. Okay, that makes sense? All right, so if you just want to name a vector, that's one thing. Now I'm going to back out those ones, and now we're just going to say it's 4, 2 again. Okay, so now I'm going to use this one, and I'm going to say, would you please tell me this? And by just putting those bars around it, I mean something, and you should know what that means. Bars around the V. Jack, what's the name for that? The magnitude of it. All right, and if this is 4 and this is 2, I hope you've gotten fast at this. Jack, what'd you get? Okay, can you give it to me before you simplified it? Okay, so that's root, and then you go this squared and this squared, so 16 and 4 makes 20. Nice, root 20, which you then simplified to root 4 and root 5, which is 2 root 5. Raise your hand if you had that one right. Cool, so that's magnitude. Next one, what about magnitude in 3D? 4, negative 1, 2. How long is that one? Jacob, don't say the answer, but tell me how.
You do 4 squared plus negative 1 squared plus 2 squared.
So 4 squared, 16. Negative 1 squared, 1. 2 squared, 4. Final answer? Square root of 21. That makes sense to you? All right, good. There's a lot of the easy stuff. That was actually like days 1 and 2, although we also added vectors. So if I wanted to add this vector, 1, 2, 3, to this vector, plus 4, 5, let's keep it simple, 6. Then the new vector is as simple as 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. And what does that mean again? The answer is 5, 7, 9. What is it? Is it a point in space? No, it's not. Remember, these are not points. Remember, these are arrows. And it would be, that could be anywhere in vector space. But we typically think of it as, if it started at 0, 0, then you'd go 5, you'd go 7, and you'd go 9. So remember, these are actually movements. They're not a place. They're where you would move to. Because your answers aren't dots. You know, when we look at this, did I draw a dot? No, I draw a movement from here to here. Okay, so the reason I'm saying that is today's job is to help you understand the vector equation for a line, and finding perpendicular vectors, and scalar products. All right, so let's make sure you get this. If I said I have the vector 5, 6, 7, and I throw a 2 out front, what do you think that does? Remember, vectors are a motion. It's going 5 in this direction, 6 in that direction, and 7 in that direction, and I think you know, now it's going 10, 12, and 14. It's not a dot. It's going from 0, 0, for instance, but it could be from anywhere. It's going 10 in the one direction, 12 in the other, and 14 in the last dimension. Okay, so do you get it? You could actually start anywhere you want. You could. This is a vector that you could start anywhere. You could start it at 0, 0, 0, and then go 10 in this direction, 12 in this direction, and then it'd be 14 back towards you, which is really hard to visualize, but okay. So let's go back to a really simple vector, 2, 3, 4. I can do that one in the room. Okay, so imagine I start at 0, 0, 0, which is the origin, and I go over 2 in the x. I want you to stare at where I should go. Try to figure it out. Where should I go in the room if I'm going to go 2, 3, 4? Over 2, up 3, and back 4, your way. Okay, so 2, 3, right on the ceiling. 4 feet on the ceiling. You should have been right about there. Does that make sense to you? Okay. Then it's a vector that goes from 0, 0, 0 to that spot. All right. So I hope then that this makes sense to you. You guys know the boards are magnetic? That I could say that this is from the point 0, 0, 0, and now this is a point. It's not a vector. And then it goes 2, 3, 4. Do you agree I haven't messed anything up? 0, 0, 0 plus 2, 3, 4 is still 2, 3, 4, isn't it? Okay, so this is a point. And you can start saying where the vector is by saying, I want you to start here and go that direction. Do you get if I wanted to, I could go that direction 2 times? Or I could go that direction 12 times? Keep going that way, 12 sets of this. So then this is a variable, and we usually use lambda. It's kind of like a funny looking H. Bent over and sideways H. Draw it with your own artistic license. Okay. Now we could, they sometimes use S for that too. And what they're saying is, if I wanted to have a point, for example, let's say I wanted to start at the point 1, 1, 1, and I wanted my vector, this is the vector part. I wanted my vector to be 5, 0, 5. That means go 5 in the x direction, 0 in the y direction, and 5 in the z direction. Then I'd write it like this, and I'd put a plus, and I'd put a lambda. There, you just learned to write an equation for a vector that starts at 1, 1, 1 this time and goes 5, 0, and 5. So where will it be at, I'm going to do a lambda, sorry, I, J, K table. Does that remind you of anything? It's kind of like the R theta table or the XY table. Okay, so at lambda is 0, I want you to think about it. If you started at 1, 1, 1 and you went 0 times in those directions, you'd still be at 1, 1, 1, wouldn't you? That make sense? If you went 1 time in that direction, you'll be at a new place. You will not be at 5, 0, 5, will you? You started at 1, 1, 1 and you went 5 in the x direction, you would go 1 plus the 5, you'd be at 6, and you started at 1, but you went 0 in that direction, means you'd still be at 1. And if I go 1 here, I go 1 plus 5 is 6, 6, 1, 6. Could you think of these as seconds? At time 0, I am at 1, 1, 1. At time 1, I would have moved to 6, 1, 6. Tell me where I'd be at time 2. So Jack, what's the easy way to say how to get that next number? What's the easiest combo of like adding? Not sure I understood that, but could I start with 616 and go from there?
Yeah, then just add
And then just add what?
5, 0, and 5.
5, 0, and 5 to that. So then final answer?
It's 11, 1, 11.
11, 1, 11. So do you get moving across the room at that point? If I started at 1, 1, 1, picture that in the room. Over 1, up 1, and then back towards you 1. Started there. Then I went in a direction. I went 5 in the X direction. And then I went nothing in the Y direction. And then I went back towards you another 5. I went to here. So I started at one point and I went to here. And then if I wanted to keep doing that, I could. Just keep doing it, keep doing it, keep doing it. You get that the Y height would stay the same the whole time. Because I'm never adding anything to the Y height. I started at 1 on the Y height, 1, 1, 1. And the middle number there, this number right here, is 0, so I just never get taller. It stays at height of 1. And it would just keep moving in the other two directions. Keep moving across the room. Okay, so here's a simple question for you. If I start at 2, 3, 4, and I go actually, I just wrote a vector, and I apologize for that. I start at point. Let's make the point -1, -1, -1, and I go in this vector direction. Write an equation for that. It's got a point. It's got a vector. You should write an equation. Just say -1, -1, -1 first. Good. What comes next? Always. Every single time. Plus. And then they can change this variable, but I bet you used lambda. That was good. And then it's 2, 3, 4. Does that make sense to you? This is where it starts, and this is where it goes. And this is how many times it goes. Think of it like time. At time 0, it's still here. Because if you put a 0 here, the 2, 3, and 4 get canceled out, and you're just going to stay at -1, -1, -1. All right. Next thing I want to review is a formula I gave you yesterday, and it goes like this. A dot, that's a dot, not a times, B equals AB, like this with the bars around them. I'm not using vectors because it takes too long. Cosine theta. Oh, what the heck, it doesn't take that long. It'd be okay if you didn't write those on the test. I'd want you to. That figures out the angle between two vectors. Let's practice that from yesterday. Here's two vectors. 2, 3, 5. That's going to be vector A. Vector B is going to be 1, 1, 1. My question is, what's the angle between those two vectors? Now, I'd like you to get it to the end, except the part where you'd have to break out the calculator, don't do that. So in other words, at the end, you're going to say it's inverse cosine of something. Okay, so can you figure out A dot B? Do you remember how to do a dot product? Taught you that yesterday. Be honest. How many of you remember it? Good, that's most of you. For those of you that didn't remember it, it's just this times this, that times that, and that times that, all added together. Then you'll have to find the magnitude of A and the magnitude of B, and times them together. And if you get it that far, I think you'd be able to finish it. So just figure out what A dot B are, the magnitude of A and the magnitude of B. And you can stop there. The part that you'd use a calculator for, you can just let that go. Pausing. Okay, I just need to remind people what we just did there. The dot product was 10. These magnitudes were square root of 38 and square root of 3. And now from there, it'd be easy to solve. You just divide by these guys and then take inverse cosine. Okay, so the reason I wanted to review that is because if I give you these two equations where this is a point 214 plus lambda 117. Do you get that that's in that form, so you should know this is a point? And you should know that's a vector? All right. So then I give you another one. This one's also going to start at 214, but it's going to go a completely opposite direction. 4, 4, 5. Would you agree that those two both share the point 214? And then they go in different directions. So if I were to, in the room here, show you, I got one of them starts at 214, 2, 1, 4, starts about there. Okay? And then it goes in one direction. And the other one goes in a different direction. So they're kind of like this. Okay? I'm not going to go exactly where they have, but there's going to be an angle between those two, isn't there? So, if you were going to do this problem, see if you can recall the formula I just had on the board a second ago and just set it up. You don't even have to finish it, just set it up. How would you find the angle between those two? If I were you, I'd start with the formula. What's the formula for the angle between the two? Let's give these guys names. Let's call them A and B. Say this is vector A. Actually put it here. Why am I putting it there? Because I don't want somebody to think 214 is the vector, because it's not. 214 is a point. Let's call this B. Well, then the formula is still the same, server. It's A dot B. And I'd be totally fine with you writing dot. It keeps people from thinking that it's multiply. Equals absolute value of A, which means magnitude of A, times magnitude of B. That is a times, not a dot. And then it's cosine of theta. So it's the same equation as before. That's the setup. Except if you're going to do the dot product, just do the dot product. It won't take you that long. Would you please figure out the dot product? That'll tell me if you really know what the vectors are. Did you get 43? And that was again 4 times 1, 4 times 1, and 7 times 5. So it's 35 plus 4 plus 4. It's 35 plus 8, 43. And then you could find the magnitude of A. Remember, that's the vector, not the 214. Okay? 214 is just a place where that vector would start at, and then it would go. Vectors are a motion going in that direction, and it would go this direction. Now that's kind of like a slope. I want you to think of these two as like a slope. What if their slopes had been the same? What do we know about lines that have the same slope? Like let's say I had y equals 6x plus 4 and y equaled 6x minus 7. They both have a different y-intercept, but they have the same slope, so they are what? Say it if you know it. Parallel. If the slopes are the same, they're parallel. Same thing with vectors. If those two things that are highlighted are the same, then they're going to be parallel. Yes, sir?
Aren't they also going to be equal then?
In this case, since they started at the same point, they're not only equal, but they're on top of each other. But I get what you mean. Even if I had started at a different point, if their slopes were the same, they would be the same vector. I agree. Because we can move them around. But if I left one starting here and one starting there, they'd have the same slopes, and then they would be the same vector but parallel to each other. So bottom line, if these two highlighted things are parallel, it's going to mean they're the same. Let me give you one like that. So here's one like that. 2, 5, 4 plus lambda. You don't have to write this down. Just listen. 7, 8, 8. And 6, 1, 9 plus lambda 7, 8, 8. Do you agree that the vector is this part? It's the same vector, which means it's what? It's the same length as each other, and it's the same direction as each other. They just have a different starting point. So they're the same vector, so wouldn't they have to be parallel? Yeah, so those are parallel. So what I'm leading to, I bet you know what I'm going next. Perpendicular, yes. What combo of numbers would make this perpendicular? It's completely different than on slopes of lines where it's the opposite reciprocal. This is not like that at all. Let's make these have 3 variables, and I bet you can't guess what I'm going to use for the 3 variables for that, and that. Oh, I'm actually saying I bet you can guess. What would be logical variables? Yes. I, J, and K. Okay, what I can tell you about this and this, if they're perpendicular, it's not like the old days when you were in 2 dimensions, when there was only one way to be perpendicular. I'd like you to think about that for a second. If we're in the old days, then the z-axis here doesn't exist. We got to stay right in here. So if I'm going to stay in this plane, how many ways can I be perpendicular? Well, it could be there, and that's it. That's not perpendicular, is it? But in 3D, if I have a vector that's, let's say, going this way, I can be perpendicular to it here. Here's still perpendicular. That's still perpendicular. That's perpendicular. That's perpendicular. There's like so many ways to be perpendicular to something in 3D space. Meaning the 2 lines will make right angles. Would be a way to say that. Okay, so how do I tell? Write this down. Perp means dot product is 0. They will be perpendicular if the dot product is 0. So, does that mean that I can just make one of the numbers 0? No, I want you to think about that. If I put a 0 here, and let's say a 1 here and a 6 there, it's, again, not like normal math where you can put a 0 in and everything turns into 0. Because we'd multiply this times this. Do you get the first thing would be 0? But then this would be 8. And this would be 64. So if I tell you 2 of them, though, I bet you could figure out the third one. And that's what we'll do. So use logic here. Do you get that 0 times the 7 meant 7? 8 times the 1 meant 8. Who knows what has to go here? Think it through. What would have to go here? I'm going to call it K. What does K have to be? Soren? Negative what?
1.
Thank you. Negative 1. When I am old, but I'm also standing right by a loud air purifier thing, so when I have to ask you to repeat, it's because of that. So I'm going to go 7 times 0 is 0, 8 times 1 is 8, and 8 times negative 1 is negative 8, adds up to 0, dot product, 0. Those 2 are what? Perpendicular. All right, I'm going to give you another one. 1, 2, 3. That's a vector. We're going to call it vector A. Question first.
If you just use a 0 vector every time, wouldn't that technically work?
You're right, if you make 0, 0, 0, yes. but that's a vector that doesn't go anywhere. Think about it. The vector is 0, 0, 0. It's like a dot. It's not a real vector.
It's an exception.
Well, I get what you're saying, but here's how the question's going to read. So let me show you one. Here's a B, and we'll say that B is 2, 1, and K. What does K have to be? All right, everybody figure it out. It's not actually incredibly easy this time. If I've got 1, 2, 3, and 2, 1, K, and they are perpendicular, you can make it be perpendicular by choosing the right K. And the numbers can be fractions. And they can be negative, of course. Did you find yourself setting up an equation? Did you find yourself going 2 plus 2 plus 3 times K has to equal 0. Do you see what I did there? That make sense? Let's solve it and see if we get it. So if we add these together, that's 4 plus 3K equals 0. 3K equals negative 4. K equals negative 4/3. Raise your hand if you had negative 4/3. Okay. Make sense? The dot product will be 0. All right, give you another one like that. Make sure you got that. I got 2 vectors. Vector V, and it's 1, 4, 7. And vector Q, which is 0, 0, P. Just to show you we don't have to use I, J, and K. Oop. 0, 0, P. What does P have to be? Now, don't just tell me the answer. Jack, how'd you get it?
0 times 1 is 0. 0 plus 4 is 0.
0 plus 0 plus
7.
7P had to equal.
0.
So then what does P have to be?
0.
Yep. Okay. All right. Dot product comes in handy now. 2 times. Once to find the angle between 2 vectors. Once to find things that are perpendicular to each other. Okay. So I want to give you a vector, vector V, and it's 4, 2, negative 1. And I want you to give you another vector, vector R, and it's going to be 1, 0, M. How could I make these 2 parallel to each other? Is there any way to do it with just changing one number? Like M can change to anything, and there's no way to make that first number be 4. I mean, this has to be exactly the same. So that'd be a trick question. There's no solution to that. Can't make those 2 be parallel. Can you make them perpendicular? Yes. Okay, next. Let's say I had the point 0, 1, 2 plus lambda 4, 2, negative 1. And I give you another vector equation of a line. Now that starts at 1, 4, 9. And it goes to lambda 4, 2, negative 1. Where do these 2 lines cross? Doge, use logic. I can tell something's bothering you about it. Use logic. Where exactly do these 2 lines cross? What do you think, Jacob?
They're parallel.
They're parallel, so they don't ever cross. Does that make sense? If they're parallel, like train tracks, they don't cross, right? Even in 3D space, if two things are parallel, they're not gonna cross. Okay, then what if I allowed this number to be Q? Could you make it so these two are perpendicular to each other? Yeah, that's the same thing as before, except you just have to know which set of numbers to use. Okay, so figure out if these two are perpendicular. I know it's very similar, but some kids are going to do it wrong. Figure out how to make these two be perpendicular to each other. Well, as soon as you say perpendicular, then I want the vectors, which is this and this, dot product to be 0. So it's back to that same question as before. So we got 16 plus 4 minus 1q has to equal 0. Negative 1q is equal to negative 20. What's q gotta be? Final answer, q is what? What? 20. Isn't it 20? Pretty sure it's 20. Did I do something wrong? People are looking at me funny. Isn't Q 20?
Yeah.
Okay, good. Just making sure, because like I had a lot of weird body language and mumbling. Okay, all right, good. So then those two now, if I change Q to be 20, would be perpendicular to each other. Where would they intersect? Because if they're perpendicular, they do intersect. Where would these lines intersect? That's the job for tomorrow. No, I have to learn it right now. But I'm going to tell you something that's important. I can write equations for this. 0 plus 4 lambda. It would be lambda 4, but I'm going to call it 4 lambda. And I'm going to use a different thing than lambda over here. I had lambda for both of them. Remember how I said it could be any variable? Let's call this s. Although I hate s's because they look like 5s. So I'm going to make it t. Okay? Then 0 plus 4 lambda would have to equal 1 plus 4t. And I'm going to highlight as I go here. 1 plus 2 lambda would have to equal 4 plus 2t. And I could set up a system of equations. And that's the punchline to how do you solve it? You set up a system of equations. All right, next I got to get you into, like, fly through some of these notes that were important, and then we'll get to the homework so we can start the homework together. All right. These are not important. If I asked you to graph this, it should have been like super easy, and we already did an angle between, so we're going to skip that. On this kind, you were supposed to find the lengths of these, which is the magnitude. So these should have been easy. I would have just changed them to like 1, 3, and then found square root of 1 squared plus 3 squared. Those are pretty easy. Unit vectors in the same direction. Well, first, a reminder of how to find a unit vector. If this is 4, 4, then I got to figure out its length. Its magnitude is square root of 4 squared is 16, 4 squared is 16, 16 and 16 makes 32. Do you agree that the magnitude is 32? A unit vector is found then by going 1 over root 32. There's my unit vector. So I forgot to review that from yesterday. Okay, and this was again the magnitude right here. So you go 1 over the magnitude in front of it. So if I got something that's 12 feet long, I go multiply it by 1 over 12. I just shrunk it down to 1 foot long. Okay, so that's a unit vector concept. We're skipping this for now. We're trying to get to the new stuff. This is, again, trying to remind people how to use that cosine formula. They're being vague on purpose to make the kid remember what it was, but we reviewed that already. This is a reminder of how to use dot products. Old homework. And now this is trying to get us into that stuff that we just learned today. So if I have, this one's really scary looking, but it's just saying if I have a point and I use lambda, and this is your first exposure to a point with lambda and a vector. Okay. Cartesian form, parametric form, and vector form are important. And so we'll do one of those problems for you. This is what we just did a second ago. Here's a point, here's lambda, and there's the vector. Does that make sense to you? Would you just look and see how they got this, this, and this from this? Look, I'll walk you through it. X equaled x1 plus lambda a. Look at that. X equaled x1 plus lambda a. Does that make sense? So if we have it in vector form, to change it into parametrics, we just basically have to multiply it out. And you know what Cartesian is? It's just another name for putting it into x, y, and z form. That's like we used to call it rectangular form. So let's do one like that together. So let's say I had the point x, y, z is 1, 2, 3 plus lambda 5, 1, 5. Can you tell where we started? We started at this point. Can you tell where we're going to go? Remember, vectors are a motion. This is where we go to. We go 5 in the one direction, 1 in the next, and 5 in the other. And so this is the vector. Vectors are a motion. They're like in motion. They're like kind of like a slope. There's my equation for it. Now, what would I get if I took this, wait, highlight, this equals that plus that. What you're doing there is you're getting parametrics for it. X is equal to 1 plus 5 lambda. Robbie, what would y equal?
2 plus, what do they call that thing again?
Lambda.
Lambda 1.
Yep, I'd say 1 lambda.
1 lambda.
Okay. And Selena, what's the last one?
Z equals 3 plus 5.
3 plus 5 lambda. Awesome. That's the vector form of it. This is the parametric form of it. Now if I solve this for lambda, lambda would equal x minus 1 over 5. This middle one, lambda would equal y minus 2 over 1, which is the same as y minus 2. And for the last equation, z minus 3 over 5. And if I said this equals this equals this, do you get I only have x, y's, and z's in it? Then it's not parametric anymore, is it? What is it? Cartesian, which is another way to say rectangular. I know that's not exactly right, but it's close enough. only got X's and Y's. Well, we happen to also have Z's because that same graphing system rectangular could have had a Z in it the whole time. All right. So your homework starts with things like that. Number one, let's do this together. You ready? I think you guys mostly would have said this, and it's going to be close to right. Plus lambda 5 negative 3. The only thing it's missing is we should really start with xy over here. I didn't want to confuse you before with that, but we're just sticking on an xy in a parenthesis at the beginning. Why? Because then it makes it all set up for multiplying it out to get parametric form. Go ahead and do that. Parametrics need two equations, an x equals equation and a y equals equation, right? Max, can you tell me the first parametric form? You're just going across the top here.
X equals 5 plus 5 lambda.
Yep. That look like parametrics? Well, it's got an x equals equation. Christine, the y equals equation.
Oh, sorry.
Can you do it?
Y equals -6 minus 3 lambda.
Yep. And then, if you solve these both for lambda, do that. And you'll get Cartesian. So it's like you're trying to solve for this. So you subtract 5 from both sides, and you get x minus 5 over 5. And you just say equals the other one. Solve this one for lambda. Y plus 6 over negative 3. And there it is. That's only got x's and y's in it. Give it a fancy name, Cartesian. I would have called it rectangular and been happy, but it's good for you to know that there's lots of different ways to say these things. Get how I got that? Just was solving the top one, solving the bottom one for lambda, setting them equal since they're both equal to lambda. All right, what if I have 2 points and I want to find the vector that goes between them? Doesn't it matter which direction I go, from what to what? Do directions matter? Yeah, they definitely matter. So we're going to say this, and let's cross this out and say to that. Well, then the vector form of it is -2, 7 is our point. And what would be wrong with just doing this and then putting the other point right there? Well, that's not the other point. That's supposed to be how you get to 3, 9. How do you get from -2 to 3? Yes?
You go over 5.
Up 5. And how do you get from 7 to 9? And there it is. Remember, this is a lot like our equations for lines before. You'd have 1 point and then the slope. Yes?
In parametric form, do you have to have lambda equals like something?
It doesn't have to be lambda, but there has to be some variable for this. You can use t, you can use lambda, you can use a lot of things. All right. And what's really missing from this is just an x and a y. And why would that be important? Because it helps when you're getting parametric form, right? So put an xy here. Because then, to get parametric form, we can just go across here and go x equals -2 plus 5 lambda. And then do the same thing across the bottom. And for Cartesian, solve them both for lambda. If you want to write lambda equals, you can, but you got to get rid of it at the end because you'll set the lambdas equal. X plus 2 over 5, and the other lambda, for this one, y minus 7 over 2, and then since lambda equals lambda, we can just say equals in between. And you really should just erase these then. And there's your answer. All right, I know that was intense, and I really hope that you practice this by doing some more of this homework. Will there be something that stumps you? Maybe. If so, look at the answer key. Learn from it. And that's all I got for you for the video for today.